phase change on PV and TV diagrams. How do we show changes in temperature, pressure, and volume on a graph during phase change? We have over here a liquid that is at a temperature below the saturation temperature. The liquid is contained in a cylinder with a freely moving piston so that the pressure of the liquid is always constant. As we heat the liquid, it'll expand a little as its temperature rises. We can show this process on a TV diagram. In this, the vertical axis is the temperature and the horizontal axis is the specific volume. Showing the heating of the liquid, we can draw a line which shows that as the temperature rises, the specific volume increases by a small amount. We label this line L to show that this is in the liquid phase. Eventually, when we've heated the liquid sufficiently, its temperature will reach the saturation temperature. At this point, the liquid will start turning into vapor. As we heat it further, more of the liquid will turn into vapor, and the vapor will expand. We can show this process as a horizontal line on the TV diagram, and this will be at the saturation temperature, Tsat. Eventually, all the liquid will turn into vapor. Now, if we heat it further, the temperature will rise above the saturation temperature, and the vapor will carry on expanding. We can show this also on the TV diagram, and we label it as V for vapor. This line is an isobar. It is a line of constant pressure on a TV diagram. Let us discuss the terminology that we use in talking about phase change. If we have liquid at a temperature below the saturation temperature, that is known as subcooled liquid. If we have vapor at a temperature above the saturation temperature, we call that superheated vapor. If there's a liquid and vapor mixture at the saturation temperature, which is in equilibrium, that is known as a saturated mixture. The extreme left of the saturated mixture line is the point where we have all saturated liquid. The specific volume of that is denoted by V sub F. At the other end, we have only saturated vapor. The specific volume of that would be given by V sub G. In the region between that, the specific volume will lie between these two values of Vf and Vg. Let us draw the isobar at a higher pressure. We can do this by putting a weight on top of the piston. The liquid is now under pressure. Because the pressure has gone up, the saturation temperature of the liquid has also increased. Now when we draw the line for the subcooled liquid, it'll extend all the way up to this new saturation temperature. At a given temperature, the specific volume of the liquid under pressure would be slightly less because it is being compressed. However, when we look at the value of Vf at this higher pressure, the Vf has increased. Because it is at a higher temperature, the volume of the liquid expands. This effect overcomes the fact that it is under higher pressure. Pressure does not have that big an effect on a subcooled liquid, but the temperature makes it expand. On the other hand, when we look at Vg, this is for the vapor. So pressure has a much bigger effect, and the vapor would be compressed, so Vg would have decreased. Let us keep repeating this at successively higher pressures. And what we'll see is that the liquid plus vapor segment over here keeps becoming smaller and smaller as Vf increases and Vg decreases. So as we keep increasing the pressure, the segment liquid plus vapor will become smaller and smaller. Eventually, if we reach a pressure that is high enough, then instead of having a horizontal segment, we will only have an inflection point. At this point, Vf is equal to Vg. This pressure at which Vf is equal to Vg is known as the critical pressure. Now, the critical pressure has some very interesting consequences. If we have vapor and liquid in a container, how can we tell just by looking as to which portion is vapor and which portion is liquid? We can tell because the light refracts very differently through vapor and liquid. The refractive index is a function of the density, and the light refracts differently in the liquid and the vapor, so we can actually see the interface between them. However, let us look at what happens if we have a constant volume compression process. So if we have this vapor and liquid mixture and we start increasing the pressure, then eventually we will reach the critical pressure. At this point, the refractive index of both the vapor and the liquid become the same. And we will see that the interface between them disappears. At this point, it no longer makes sense to talk about a vapor or a liquid. We have only a single phase in our system, and this is known as a supercritical fluid. Let us draw a complete set of isobars on a TV diagram. Then we draw a curve through all the turning points on these isobars. This curve is known as the vapor dome. So we draw the vapor dome by itself on a TV diagram. This vapor dome represents a phase diagram, which separates the different phases that can exist. Underneath the vapor dome, we have the conditions at which a saturated liquid-vapor mixture can exist. To the right of it, we have superheated vapor. On the left, we have subcooled liquid. If we then draw the critical pressure line, everything above that is supercritical fluid. The peak of the vapor dome, where the critical pressure isobar meets it, is known as the critical point. The volume at the critical point is known as the critical volume, and the temperature is known as the critical temperature. We can also show phase change for a system which is at constant temperature. Here we have a vapor in a cylinder. This is at a pressure which is lower than the saturation pressure. We start compressing the vapor. We can show this process on a PV diagram. The axes over here are the pressure and the specific volume. The compression of a vapor would be shown by this curve, which extends up to the saturation pressure. Once the saturation pressure is reached, the vapor will start condensing and turning into liquid. As we compress that, the volume will decrease as the system is compressed further. The compression of the liquid plus vapor is shown by this line at the saturation pressure. Finally, all the vapor would be compressed and have turned into liquid. The compression of the liquid then can be shown by a line on the PV diagram. This line that we have drawn is a line of constant temperature, an isotherm. If we draw all of the isotherms on a PV diagram, then we can draw a curve through the turning points, and this represents the vapor dome. As we carry on increasing the temperature, eventually we will reach the critical temperature. The critical isotherm passes through the peak of the vapor dome. If we draw the vapor dome by itself on a PV diagram, then the area underneath it is a saturated mixture. To the right of it is the superheated vapor. To the left is subcooled liquid. And if we draw the critical isotherm, then the region above that is all supercritical fluid. The peak of the vapor dome is the critical point. The volume over there is the critical volume, and the pressure corresponding to that is the critical pressure. To summarize, phase change can be shown on either PV or TV diagrams. A substance can be a subcooled liquid if its temperature is lower than the saturation temperature, superheated vapor if its temperature is greater than the saturation temperature, or a saturated mixture, in which case its temperature must be equal to the saturation temperature. At the critical point, the properties of the liquid and vapor become the same, and the substance becomes a supercritical fluid.